constant coefficients with an example where we model a mass spring damper system. Now, mass spring damper systems can be found in nose gears, in the vertical direction, but also to avoid shimmy of the nose wheel. They can be found in helicopter struts and also. So the way it is configured is we have some kind of mass attached to a fixed base by a spring and a damper. We have a spring constant K, we have a damping coefficient B, and we have a mass M. Well, to analyze this problem, I'm going to use the framework of dynamics, where we have a free body diagram, an axis, and the equations of motion. So let's start with defining the positive y direction in our case, which will be a function of t. And let's write up our free body diagram. So we will have four forces here, because the idea is that we will have an external force F. We have two forces already. So one is our external force F, and we also have gravity. And if we move our mass in the positive y direction, we get two other forces, and we get a force B, a damping force, which acts in the opposite direction, and we get a spring force, which I'll do in green. A spring force going in that direction as well, and I am going to not write F like that. I'm going to write F. Now, so we have a free body diagram, an axis system, and we have the equations of motion, which is the second law of Newton. Sum of F is equal to the mass times acceleration, where we know that acceleration is the second derivative of the position. We also know that the velocity is the first derivative of the, displacement or position. If we look at all these forces, so we have our damping force, Fd, that's right, is equal to minus B times V. We'll have our spring force, which is minus K times Y. And we have our gravitational force, which is M times the gravitational constant, which is also in a downwards direction. So if we write this all down in this equation, we get minus M times G minus K times Y minus B times V is equal to M times A. So this is our physical system. Let's plug in y dt squared, so the second derivative for A, and we find that we get minus F minus M times G minus K times Y dt is equal to M d squared Y dt. This here is a second order differential equation. Let's write it out. So I will move this term, I will move this term also over there, and then switch the whole thing round. So we get m d squared y dt squared plus b dy dt plus ky is equal to f minus m times g. Order differential equation with constant coefficients, and if we have a force here which is in total non-zero, then it is an inhomogeneous equation. But we see that if we start with a relatively simple physical system, a mass spring damper system, that we get to a second order linear differential equation. Now we will work with these in the when we look at modeling. This will be the focal point, or one of the main focuses, when we look at stability and system properties in automated flight in Block 8.